The first step is we are going to just copy our original system down exactly as given to us and call that system 1. So we have our bracket and 2 inches to here. And 1.5 inches. And we have these 2 forces being applied at the end here. A 15-pound force, and we are given its dimensions with a ratio triangle. And a 20-pound force, 30 degrees from the vertical. That's our original system. Our simplified, or our equivalent system, it's that same object. However, in the simplified system, we are only having 1 force and 1 couple, and those are both acting at point O. The force I'm going to break down right away into its components, which I'll call Fx and Fy. And the couple, I will assume, is in the counterclockwise direction. Again, you don't have to follow those assumptions, but I think it's easier to start this way, and then at the end we can redraw it in the correct direction if we need to. In this case, we have 2 forces and no couples. Our simplified system will have 1 force. It has 2 components, but it's really just 1 force and a couple. And in the end, I'll draw this in its polar form. Questions on drawing our original system and our simplified system? They're going to share the same coordinate system. So with the equations, I'm going to start with the forces. Looking at my system number 1, I'm going to find all the forces that act in the x direction and sum them. Again, this is not an equilibrium. I cannot say this is equal to 0. I have to fill in what the right-hand side is. So in equation number 1, what should my right-hand side be based on system number 1? 4 over 5 times 15. Right, so that's the horizontal component of the 15-pound force. So just like we looked at in when we were dealing with particles, we're just looking at x components of forces here. And we're adhering to our coordinate system. I said x right, y up. So the 15-pound has a positive x component and a positive y component. The 20-pound will have this negative x component, but a positive y component. We were given that the angle to the vertical of 30 degrees, so for the x, I had to use sine 30. I can add this up and get whatever the net force is in the x direction. In this case, we get 2. I put that aside for the moment, and now I look at system number 2 and add its forces together that are in the x direction. Because of the way I wrote my force already in its component form, this is very easy. The only force in the x direction in picture 2 is Fx, the x component of that force. Because my goal is to make these equivalent systems, the sum of forces in x1, the sum of forces in x2 are equal. Therefore, Fx will also be 2 pounds. So just from here, I found what the x component of my equivalent force must be in system number 2. Now, once we have both forces in the couple, we're going to be able to rewrite this in polar form, so that it would just be 1 force at some orientation. Now I do the same thing in the y direction in system 1. Again, I have 2 forces. I'll have 3/5 times 15. And the vertical component from the 20 is 20 cosine 30. They're both positive. They come out to 26.3 pounds. Now the easy part is looking at system 2, the simplified one. In this picture, I only have Fy. I assumed it was positive. I get Fy is then 26.3 pounds. These are the straightforward steps. The forces are easy. The moments is where we have a little bit of choice of what to do. I have Fx, I have Fy, I need to find C. So I get to choose here at what point I want to take the moment about, but whatever point I pick, it has to be the same for both systems. It doesn't matter which I pick. It could be point O, nothing else has a label here, but if I call this point D, and let's just call this point B for now. But it could be any of these other points as well. I want mathematically to make it as easy as possible. Looking at D, because these things are happening at angles, it's actually easier to take the moment around D in both pictures than the moment O in both pictures. Because again, if I take the moment around O here, I will have a horizontal vertical component of this force that's going to contribute to the moment. I'll have a horizontal and vertical component of this force that contributes to the moment around O. So there'll be four things I have to worry about. Especially in this case, I'll take that back. Point D for both pictures will be easier. Where it makes it a little bit more complicated is now Fy and Fx will have components around D. So mathematically, D is a better choice. But if we did point O, we will get the same answer in the end. But the trick is I have to choose the same points in both. And D is better in one, O is better in two. I'm going to go with D. If I look just at picture one, what will contribute to the moment around point D? So both of these forces have a line of action that passes through D. But again, what was the rule? If its line of action passes through the point, since I'm taking the moment around D, right, this will not have any moment contribution around D. It would have around O, but does not through D, and the 20 also does not, because again, their perpendicular distances are 0. So neither force has a moment contribution around D. So what is the net moment in picture 1 around point D? Right, it is 0 in this case. Again, this is not an equilibrium. It turned out to be 0. It didn't have to be 0. If I took it around point O, I would have gotten a non-zero answer for the moment around point O. So actually, picture 1 was very easy. It turns out 0. But now I have to consider picture number 2. But the same point. I already know it has to be equal to 0. But now I have to fill in the right-hand side based on the picture. So what will contribute to the moment around point D in picture 2? Right, Fy has a distance, a non-zero distance from D, as does Fx. So the force Fy, I have to multiply by its distance from point D. So that will be 2 plus, it'll be 6 cosine 40 plus 1.5 to go from where this force Y is to point D. Again, that's this distance. And according to my picture, and that's where these equations come from, according to this picture, around point D, will Fy create a positive or a negative moment? Right, it's going to be clockwise. That's going to be negative. Right, and then Fx will also have a contribution. I'll put it below here. So Fx times its perpendicular distance to D. Well, to get from where Fx is being applied to where D is, I have to move 6 sine 40. And looking at the picture, will Fx create a positive or negative moment around D? So again, if we hold it at D, if we push in the direction of Fx, this whole thing would spin counterclockwise around point D. So according to the picture, this is positive and this is negative. At this point, now I can use this information. I know that Fx is positive 2. I know that Fy is 26.3. Oh, I forgot one thing in the moment equation. I'm not done with it yet. What else contributes to the moment around point D? The couple C. So solving equation 3, the value for C is negative 205. This is going to be in pounds times inches. And I drew originally my forces as in components, or the components of my force. I see that it's in quadrant 1 since it has a positive x and a positive y component. So now I'm going to draw it in polar form. And I'm going to find its magnitude and its direction. Right, how do I find the magnitude of this force, this one equivalent force at O? Right, we found its components already. Its magnitude is just the square root of the sum of the squares of that x component and y component. And that turns out to be about 26.4 pounds is the magnitude of this one force at O. And the angle that makes with the x-axis we can find because we know its horizontal component was 2. Its vertical was 26.3. This will be the angle it makes with the positive x-axis. So we can use arctan of opposite over adjacent, which tells us that this angle is going to be much steeper than it doesn't have to be a scale, 85.6 degrees.